Assalamu alaikum dear students, welcome to the online lecture on MATLAB simulation of control systems. Today we are going to discuss a filtered high gain observer for uniformly observable systems. This observer has been proposed in a paper published at the Journal of Process Control, and it's a fairly recent paper published in 2020. So in this paper, the type of, as usual, we are not going to go into the details of the paper. Rather, we are going to look at how do we implement or simulate the proposed observer in the paper using MATLAB, so that those who want to do research on this topic, they can start from simulating this observer in MATLAB, and then they can play around and do more research and do more analysis on that. Okay, so the type of systems that are discussed in this paper are basically x dot equals some function f, which is a nonlinear function of control and state, times x of t, which is the state variable. So x dot equal f times x plus some phi function, which is also could be potentially nonlinear function of control and state, plus this b matrix times the disturbance epsilon, and the output is y is equal to cx plus some measurement noise w. Here, if you look at the shape of the f matrix, it's basically it has sort of an upper triangular structure where the main diagonal has zeros, and the blocks above the main diagonals have these functions f1, f2, and up to so on f of q minus 1. Q is the total number of state variables, and then each of this fk should depend only on the first k state variables and the control. That's the constraint on the type of the systems that are that are within the scope of this research paper. Similarly, this is the structure of the phi function, which is basically could be any nonlinear function of control and state and having q elements. Then the structure of the B matrix is such that the disturbance enters through the last few state variables. So identity matrix of size nq, that is the final element of B matrix. All the other elements are zero matrices of zeros, and the C matrix is such that the first few states are being measured and all other states are not being measured. Alright, so there are some assumptions on the state and control input to be bounded, and each of these functions phi and f are also assumed to be Lipschitz continuous and uniform in the control input. With respect to the control input, the unknown uncertainty and the noise are also assumed to be bounded. And then this is one of the previous observers. This is also a high gain observer which is proposed in some reference papers cited here, where the estimate of the state is given by the copy of the state dynamics plus this correction term, which involves this P matrix, which is basically the solution of Riccati equation given here with zero initial conditions, and then the delta inverse is some sort of a diagonal matrix with some entries involving this parameter theta. So the authors, based on this previous high gain observer, the authors have proposed sort of a new high gain observer which involves a filter as well. So this high gain observer does not just involve the state estimate dynamics involving f times x hat plus phi, which is the copy of the system dynamics, plus this theta is like it's instead of the correction term here, they have this theta times k times eta, where eta is sort of like a additional filter with its own dynamics within the high gain observer, and it has the following dynamics proposed by the authors, which involve this correction term, where C transpose is this sort of a matrix, and A matrix in the dynamics of eta is again upper triangular type matrix. Okay, so after proposing this type of observer, the authors prove some results which we are not going to go into the detail, but we are going to go into the details of this numerical example that is proposed in this paper. And in this example they have developed a state space model of let's see, that's a very difficult name, phytoplanktonic growth model. So there's a phytoplanktonic growth model that has been used as an example, application example for the proposed observer. So this is the conversion of the state space into x1 dot, x2 dot, x3 dot. The output is x1, and then they also convert this into change of coordinates. So from x1, x2, x3 coordinates, they the authors convert it to z1, z2, z3 coordinates, and within z1, z2, z3 coordinates, the structure of the system is now in line with the scope of the paper, like after change in coordinates, the new state space system comes into this type of configuration, where f1 and f2 are given in the paper, phi1, phi2, phi3 are also given in the paper. So let me show you these. So this is f1, f2 and phi of u comma z, and later on you can get back the states x1, x2, x3 from z1, z2, z3 using these formulas. This is the inverse transformation. Okay, so without further ado, we start looking at the MATLAB code regarding this example, this phytoplanktonic system, a growth model. So we have to create a MATLAB function for implementation of the dynamical equations of motion. So what we do here is that first of all we define z to be x1, x2, x3. So the first three state variables in our code will be z1, z2 and z3. So I have defined the z vector in my code. Then we define the x hat, because we are going to estimate, we are going to implement the filtered high gain observer for this system of z1, z2, z3 in the paper, in our MATLAB code. So these x hat will be the three estimates of x1, x4 will be the estimate of x1, x5 will be the estimate of x2, and x6 will be estimate of x3. Then we have eta variables, which are also part of the filtered high gain observer proposed in the paper. Eta will be eta 1, eta 2, eta 3. In our code, x7 is eta 1, x8 is eta 2, and x9 is eta 3. Then we have this because if I take you back to the proposed observer in the paper, here is the so this is the proposed observer in the paper. If you look at that, there are some x hat states, eta states, and within the eta states, within the x hat states, this matrix K, this comes from, K is the diagonal of C, diagonal matrix, where each entry is P times C transpose, and P is the solution of this Riccati equation. So we need to solve the Riccati equation in our code as well. So the Riccati equation matrix in our case will be 3 cross 3 matrix because we have 3 states. So x10, 11, 12, 13, 14, 15, 16, 17, 18. So x10 to x18 will be the 9 state variables which will formulate the P matrix or the Riccati equation matrix. And we are going to implement this Riccati equation in our code as well, which is equation 13 in the paper. So if I go back to the code, then we have some constant values that are given in the paper, a1, a2, a3 and t0. These values are given in the paper. So it's that's given. So this is the a1, a2, a3 and the value of the control input for the system is also given. The t0 is given to be 1/3. The unit of time is days, does not matter as long as it is uniformly same unit throughout the whole system. Then we have this equation of u comes right from the paper, and then we have the value of theta and delta. So the value of theta and delta are given. So here somewhere theta and delta are used to be 5 and 7. In some cases theta and delta are used to be 3 and 5. Well, once you learn how to write the code for the system, you can play around with the values of theta and delta and figure out by yourself what the best values of theta and delta are. I have used the values 5 and 7 in this code that I have written. Then you have to write the values of f1 and f2. If you go up there, so f1 and f2 values are given for the given example in the paper. So if we go here, so this is the f1 and f2 right from the paper. And then we have so we have to copy these f1 and f2. So these are f1 and f2 in terms of z1 and z2, but then we have to have copy of f1, which is f1 hat, and f2 hat, which is going to be used in the dynamics of the state estimates. So in this we use x hat 1 and x hat 2 instead of z2 and z1. And then we need to have this phi, which is also given here, a2 minus u times z1 and so on. So this whole line is the value of this vector phi as it is given in the paper. And then we need to make a copy of a phi in terms of x hat. So in phi h, instead of z1 we use x hat 1, wherever there is z2 we use x hat 2. So this is the copy of the phi for the state estimates, for the dynamics of the state estimates. Then we have formulate the f matrix 0 f1 0 0 0 f2 and 0 0 0. This is the same structure that is given above here in the paper. So here you can see here that this is the structure of the f matrix that we formulate, and same we do in our code. And then we have the same thing for the state estimate dynamics, f hat 1 and f hat 2 we use here. And then we have the C matrix because we are measuring x1, y is equal to x1, so C is going to be 1 0 0. So remember this, the x1 is equal to z1 in this paper. So if you go to the paper here, here this says y is equal to x1, and here it says z1 is equal to x1. So since we are writing the code in terms of z, so y is equal to c times z, which is y is equal to z1. Then we have this A matrix. This A matrix structure is given in the paper here. If you go above to the observer equations, so this is the A matrix. The entries above the diagonal are the identity matrices of appropriate size. In our case, that size is 1 cross 1, so that's the A matrix, and CQ is this 1 0 0 as given in the paper. And then K is the diagonal P times C transpose. So P times C transpose, this is a vector of probably 3 cross 1, so diagonal matrix will be 3 cross 3. K will be a diagonal matrix of 3 cross 3, which will be using the solution of the Riccati equation. Then Z dot is F times Z plus phi. I have not included the disturbance here. So here if you look at the dynamics of the system discussed in the paper, x dot is equal to f of f times x plus phi plus b epsilon. So I have not included b times epsilon. You are most welcome to use this in your own research. The B matrix will be 0 0 1. It will be a 3 cross 1 column vector in this example, and epsilon can be any bounded function of time. And then you can use x hat dot equals f hat that we created here for x hat and plus phi. So this is from here the dynamics of the proposed observer. So if you look at that, here x hat dot is equal to f times x hat plus phi times x hat minus theta times k times eta. So that's the same equation. And then we have eta dot is equal to delta times theta minus eta plus theta A transpose eta plus CQ transpose and so on. So this is the same this term. And so here this is cx hat minus y, that's it. But this is some additional term which is proposed in the equation 20 of this paper. So if you go to the equation 20, there is a slight modification in the dynamics of eta, c x hat minus y plus alpha, and where alpha dot is equal to minus theta delta theta times k1 and eta 1, which I have written here. But I have run the code without this and using only the observer proposed above without the alpha. There's not much difference in the results, but anyways I have included this. So next there is P dot. This is the Riccati equation. If you go back to the proposed observer model, so this is the Riccati equation, and this is what I have written here. So remember that this P is a 3 cross 3 matrix, so P dot is also a 3 cross 3 matrix. So you have to be careful when returning the values. So finally we return all the values, and when we return the values, the first three variables, state variables, are z1 z2 z3. So we make dx equal to z dot. The next below z dot is x hat dot, below that is eta dot, and below that is the first row of P dot. This is the first row of P dot. Then you have to take the transpose to make it a column, because dx is a column vector of 18 entries. So you have to keep the arrangement of the states appropriate, otherwise there will be some errors. So at the least you can just copy my code, take a screenshot of the video, for example here, pause the video here and take a screenshot, and then you're all set. Rewrite this code by yourself, and that will increase your confidence about writing MATLAB code for the simulation of control systems. This is the transpose of the second row of the P matrix. This is the third row, the transpose of the third row of the P matrix, and that completes the code. And now we have to run this code. So in order to run the code, I've already written the script file. So this is the script file where this is the ODE45 command, which calls the function that we just discussed, and I run it for like 5 days because the unit of time in this example is days. And then we give some initial conditions to z1, z2, z3, and some initial conditions to x hat 1, x hat 2, x hat 3, and all other initial conditions are 0. So initial condition for eta, initial condition for the Riccati equation matrix P, all of them are 0. So in total there are 18 state variables in this model that we have discussed. So there will be 18 initial conditions, and then you will plot well, I have plotted the x1, which is z1, and its estimate, and then I have plotted 1 over z2. 1 over z2 is x2. If you look at here, so here if you look at the equation number 27, so z1 is x1 and x2 is 1 over z2. So I have plotted z2, and the estimate of z2 will be 1 over x5. So this will be the all rows and fifth column of the x that you get from ODE45 function. And similarly 3 and 6 will be x3 and the estimate of x3. So if I run this file, change directory. Okay, so these are the results. You can see here that these are the results of x1. So blue line is the vector at the state variable x1, and the dotted red line is the estimate of x1. So estimate of x1 asymptotically converges to the x1 itself, and similarly this is the x2 and the estimate of x2, and similarly this is the x3 and the estimate of x3. You can see that the estimate is converging to the actual value. I have not used any measurement noise, or if you want to use measurement noise or the disturbance in your code, then you can add here, you can add measurement noise here plus w, and you can define the w to be any function of time which is bounded or a constant value. If you want to add some disturbance here, you can add here some some b times epsilon. So b will be 0, 0, 1. It will be a single column and 3 rows, and epsilon can be any constant or function of time as long as it is bounded. And well, that's it for this video. I hope that you are now able to simulate this finite filtered high gain observer, at least for this example that we have discussed from the research paper. For more upcoming videos, you can subscribe to this channel. If you want to be notified, you can also hit the bell icon. Anyways, but I'm planning to complete lectures on linear control systems. I already have lectures on linear control systems on my channel. There are some initial lectures missing, so once I complete that playlist, you can have the whole course. If you want to complete a course on control systems at undergraduate level or revise the course, you can use the channel. Well, thank you so much. That's all for today.